Bending to pick a target off the floor requires continuous, dynamic cooperation across every single joint in a humanoid frame: the legs, torso, arms, and hands. Until now, no single AI model possessed the mathematical capacity to manage that entire, highly complex kinematic chain simultaneously. Gemini Robotics 2 solves this by deploying a unified vision language action, or VLA, model that drives the robot's entire body directly from its feet to its fingertips. When tested in the real world, this model successfully picks targets from the floor exactly 45.7% of the time. This success rate is the honest frontier of physical AI. Navigating unstructured physics is far harder than pre-programmed demos suggest. To scale into unpredictable environments, a robot cannot rely on narrow, memorized task sequences. It must continuously reason through every single micro-movement. Scaling requires a model that ingests complex multimodal inputs, specifically vision and language, and translates them instantly into physical action. Solving this specific whole-body friction point at scale is the exact barrier holding back the transition from narrow automation to general-purpose physical AI. Whole-body coordination requires splitting the computational load across 3 distinct models. This diagram maps out that 3-tiered software architecture, linking a primary VLA, an embodied reasoning model, and an on-device execution layer through cascading data streams. Layer 1 is Gemini Robotics 2, the primary VLA. It serves as the core translation layer, converting incoming pixel and language inputs directly into motor commands. Layer 2, Gemini Robotics ER2, acts as the high-level brain. This embodied reasoning model is responsible for multi-step task planning and broad semantic understanding of the physical environment. ER2 tracks progress over tasks lasting several minutes, pinpoints when key events occur, and orchestrates multi-robot collaboration to execute workflows a single robot cannot complete alone. Layer 3 is Gemini Robotics On-Device 2. This is the execution layer, heavily optimized to run locally on the physical robot's internal silicon. Executing on-device guarantees zero network latency, which is a hard physical requirement. Relying on cloud connectivity during real-time balancing will result in catastrophic mechanical failure the moment a single packet drops. The architecture integrates strict physical safety constraints, which are evaluated using the Asimov Agentic Safety Benchmark. The ER2 agent resolves real-world uncertainty by calculating when a requested task is physically impossible, allowing it to proactively request human intervention or outright refuse unsafe tool calls. Decoupling the high-level semantic reasoning of ER2 from the sub-millisecond reflex execution of On-Device 2 solves the latency bottleneck currently limiting physical AI. We can map the performance boundaries of the VLA by examining raw success rates for macro movements, starting with the Apptronik Apollo 2 Humanoid equipped with standard Inspire hands. This chart maps out spatial targeting success on the Apollo 2's upper body kinematic chain. It shows that the lowest friction spatial task, picking an item from a standard shelf, achieves a 76.3. Lowering the entire chassis introduces compound errors in balancing the torso and legs, exponentially increasing the failure rate. If you want the next breakdown of these unvarnished success rates the day it lands, subscribe to the channel. Moving away from humanoids, we can examine non-humanoid macro movements using the Franka Duo by-arm platform. This comparative by-arm visualization shows the baseline success rate for general pick-and-place operations on the Franka Duo sits at 74.2%. In contrast, precise insertion operations on that exact same hardware can be highly optimized, peaking at an 89.6% success rate. The data confirms that localized spatial targeting for arms and insertions is rapidly maturing. Full gravity kinematic balance remains the primary mathematical bottleneck in robotics. Moving from massive whole-body balance down to a microkinematics of fingertips introduces an entirely different set of physical problems. The Sharpa wave hand on the Apollo 2 utilizes 22 independent degrees of freedom to articulate 5 fingers. Calculating force vectors for 22 joints is mathematically far more volatile than operating a standard 2-finger pincer. Looking at this bar chart visualization of the 22 degree of freedom hand, we see that for highly specific, task-trained actions, like unscrewing a light bulb, the model reaches a 92% success rate. Yet for generic, untrained multi-finger manipulation, the success rate collapses to a range between 32 and 44%. The gap between a 92% trained execution and a 32% generic execution represents the absolute bleeding edge of current industry capabilities. The failures occur during physical actions that require dynamic grip adjustments, such as attempting to seal a Ziploc bag or tie a knot. The system struggles to map visual intent into delicate physical force without the aid of tactile feedback. A single millimeter of overtorque snaps a string or crushes a plastic seal. Because of this, standard two-fingered parallel grippers currently perform complex tasks like tight packing more reliably. They simply have fewer degrees of freedom for the model to calculate. Navigating a room is a solved spatial problem. Generic, untrained manipulation of unstructured, delicate objects will be the ultimate test of artificial general intelligence in the physical world. The on-device 2 layer introduces a final capability that alters the economics of robotics development: few-shot motion transfer. This split-screen schematic illustrates how the system abandons the traditional requirement of retraining an entire neural network from scratch for every new robotic chassis, instead mapping data from the Apollo, Franka, and DeepMind hardware back to one unified central node. The data cost for this transfer is exceptionally low. The model requires fewer than 200 data examples to map its physical intelligence to a completely new body. The time cost is equally minimal, with the local adaptation process completing in just a few hours. This transfer protocol can cross massive physical variances, successfully mapping latent kinematic understanding from a 22-degree of freedom humanoid hand directly into completely different two-finger platforms like the DeepMind or SO101. This capability decouples the intelligence layer, the brain, from the physical hardware, the body. The macroeconomic reality of this decoupling is that bespoke, highly trained intelligence is no longer the scarce, limiting factor for hardware companies. Because the software can adapt to entirely new physical constraints in a single afternoon, robotic hardware itself is rapidly being forced into an interchangeable commodity. The question now is what happens to the global physical economy when this motion transfer protocol scales to thousands of entirely unstandardized robotic embodiments. The gap between theoretical research papers and working physical prototypes has just been closed. This is Cynthia Glabs.